Hello, historical geology students. This is the fourth and last video for this week of January the 18th to January the 23rd. We're still on chapter number 1, and hopefully you've already, before I get started, hopefully you've already contacted your lab partners. If you have not contacted all of your lab partners or they don't respond to your emails, let me know and I'll call them for you. Share your cell phone numbers with your lab partners. I'm going to send you your first lab to you on Monday, and you're going to work with your lab partners. And please send in your answers through email to both my email addresses, aclee1234@yahoo.com and lee@roanstate.edu, and send it back in Microsoft Word format so I can grade it and send you back your graded labs. You got to share cell phone numbers with your lab partners so you can text each other or FaceTime each other. And if you meet in person, please stay socially distanced and all to be safe. So, without further ado, let's go on to this last part of the lecture for this week. Here you can see a diagram, and what this diagram is showing you is how later on we're going to talk about plate tectonic theory quite a bit. Plate tectonic theory first came into being back in the 1960s, and it changed geology because prior to the advent of plate tectonics, the majority of geologists knew that we have earthquakes on the edges of the Pacific Ocean in the so-called Ring of Fire. You know what the Ring of Fire is? It burns, burns, burns along the edges of the Pacific Ocean because of volcanism. But we didn't know why we had volcanoes along the edges of the Pacific Ocean or in the Mediterranean area. We knew we had earthquakes in California and Japan and in Turkey, but we didn't know why. We knew we had mountain ranges that formed on the edges of continents mostly, but we didn't know why. Plate tectonic theory gave us the why. It tells us why we have volcanoes where they are, why we have earthquakes where we have them, how mountain ranges form, and it completed our knowledge of Earth history. So, if there's one theory that's you could say is the most important theory to understand in geology, it's plate tectonic theory. So look at this picture here in front of you, and in the blue you have oceanic plate. Here with this stippled pattern is continental plate. Remember, we use the term lithosphere. The plates are lithospheric plates. So the continental lithosphere contains the continental crust in the uppermost part of the mantle. The oceanic lithosphere, here in blue, includes the oceanic crust underlain by the uppermost part of the mantle. Here, this whole layer here is the rest of the mantle in this reddish color. Here is the outer core, and here's the inner core. And this is seawater on top of the oceanic lithosphere. Here you have a deep ocean trench. What's the deep ocean trench? This is the deepest part of the ocean. It's a deep canyon on the edges of primarily the Pacific Ocean. For example, off of our U.S. West Coast, the Canadian West Coast, the West Coast of Asia, the West Coast of anyway. So you got when you have these deep ocean trenches, it's very, very deep. It's sometimes 3 to 5 miles deep, or 5 to 10 kilometers deep. These blue areas here, these blue arrows you can see, are moving away from a feature called the mid-oceanic ridge. What is the mid-oceanic ridge? The mid-oceanic ridge is a mountain range that we find in the middle of the Atlantic Ocean and the Pacific Ocean and the Indian Ocean. And what these blue arrows show you is that the oceanic lithosphere is moving away from the mid-oceanic ridge like two conveyor belts, one going west and one going east. When the oceanic lithosphere collides with the continental lithosphere, always the oceanic lithosphere will sink deeper into the earth. But instead of saying sinking deeper into the earth, geologists say the oceanic lithosphere subducts underneath the continental lithosphere into the lower parts of the mantle. These red arrows show you convection cells. Convection cells. Now, what are convection cells? In order to understand that, we have to understand something very basic about our planet. The deeper you go into the earth, the hotter it gets. For example, if you work in a gold mine in South Africa, you might be working 2 miles underground. It gets so hot down there that they have to have special air conditioners built so the miners don't die of heat exposure. So where does the heat in the mantle come from? It comes from radioactive decay, natural radioactivity in the earth. And that causes the heat to rise. You can see how it rises here near the mid-ocean ridge. And then it goes back down and it rises again. And here you have another convection cell. Or it rises away from the mid-ocean ridge and it sinks back down where you have subduction or a deep ocean trench. These convection cells can be imagined if you think about this. Imagine that you put a pot of water on your stovetop and you wanted to make beef stew. First you pour in the water. Maybe you pour in a gallon of water into your pot. And then you add your carrots and your potatoes and your beef cubes and celery or whatever you want to put in it. And you turn on the gas or you turn on the electricity, and you're going to see if the pot, let's say the pot is see-through, it's glass, you would see that the carrots and potatoes and everything are going to rise, and then they're going to sink back down, and the stew is going to churn. That's convection. Convection is a way of moving heat around in these convection cells. So what causes plate tectonics to occur is the heat in these convection cells rising and pulling apart the oceanic lithosphere so that it moves away from the mid-ocean ridges of the world like two conveyor belts, one going in one direction, one going in the other direction. But this oceanic lithosphere, it moves towards the continents. Please don't forget that the oceanic lithosphere is denser than the continental lithosphere. So wherever the oceanic lithosphere collides with the continental lithosphere, it'll be the oceanic lithosphere that subducts deeper into the earth. And this subducting oceanic lithosphere, as it sinks deeper into the earth, is going to melt because it's very hot down here in the middle of the mantle. And so then you're going to make volcanoes. As this as this oceanic lithosphere melts, it's going to make magma, or liquid hot rock. And this liquid hot rock is going to want to rise because it's buoyant compared to the surrounding solid rock. And it's going to erupt onto the surface of the earth in volcanoes. And lava will spew out onto the earth. So liquid hot rock is magma, and it forms deep in the earth. And this magma, if it reaches the surface of the earth, it's called lava. And the lava will flow onto the sides of the volcanoes. So why do we have volcanoes along the edges of the Pacific Ocean in the Ring of Fire? It's because of this subduction of the oceanic lithosphere at these deep ocean trenches. So these deep ocean trenches mark the spot where the oceanic lithosphere subducts underneath the continental lithosphere. Why do we have earthquakes in Japan or the west coast of North America? Well, imagine this is North America and this is Japan, for example. It's because we have earthquakes because the plates are colliding together, they're pushing together, and that makes stress. What is stress? Stress in physics is force divided by unit area. Stress is force divided by unit area. It's measured in PSI, or pounds per square inch, in the United States. The rest of the world measures it in kilograms per square meter. But bottom line is the rocks are being stressed and they're making earthquakes. That's why we have earthquakes in California and in Japan. It's because of subduction. Don't worry, we're going to go over this in more detail. We have a whole chapter on plate tectonics. Oh, one more thing before I move on. So basically the plates move away from the mid-ocean ridges, or they diverge, they move away, and they converge at the deep ocean trenches. In 1967, a great American scientist by the name of Tuzo Wilson, T-U-Z-O-W-I-L-S-O-N, made this map of the world. So I just wanted to summarize the names you want to remember for the first test that have to do with plate tectonics. The first person you want to remember is James Usher. James Usher came up with the theory, believed in permanentism, that the Earth's landforms have never changed and they're permanent, and they were formed 6,000 years ago. The first person to really break that line of thought was Alfred Wegener, who in 1912 came up with a theory of continental drift. And Alfred Wegener said, no, permanism is wrong. The continents move. The continents move. They were in different positions in the past. That would lead to Harry Hess and Robert Dietz coming up with the theory of seafloor spreading. And we talked about the seafloor spreading as it moves away from the mid-ocean ridges. They were the ones who determined that oceanic lithosphere moves away from the mid-ocean ridges, and the continents move too because they're in the plates. And that would lead to, and that was 1962. So that's the theory of seafloor spreading, which would lead to 1967 and Tuzo Wilson, who coined the word plate tectonics. In 1967, Tuzo Wilson brought together Alfred Wegener's theory of continental drift with Harry Hess and Robert Dietz's theory of seafloor spreading. He combined the two to make the new theory of plate tectonics, and that was the death knell. Those are the nails in the coffin for the old ideas of permanism. So if you go to any university in the world, no one talks about, no one believes in permanism. All modern geologists believe only in plate tectonics. Here's the map of the world produced by Tuzo Wilson, showing you all of the plates that we know of in the world. Here's, for example, this whole thing here is the North American plate. Here's the Eurasian plate. Here's a tiny plate called the Adriatic plate around Greece. Here's the South American plate, the Nazca plate, the Indo-Australian plate, the Philippines plate, the Antarctic plate. So the world is divided into these lithospheric plates. What are these red lines then? These red lines are called plate boundaries. Plate boundaries are places where the plates meet. For example, here you can see the North American plate here meets the Eurasian plate here at this red line right here. The African plate meets the North American plate at this plate boundary here. The South American plate and the African plate meet right here at the Mid-Atlantic Ridge, where this plate at this red line at this plate boundary. Now here's the thing you want to remember, ladies and gentlemen. Wherever you have a plate boundary where the plates meet, where you have these red lines, you have stress. Stress is equal to force divided by unit area. What is stress? Well, let me see. Here's a table here. If I push down on this table, I'm putting stress on this table, right? If I put enough stress on this table, if I was a 300-pound lineman for the Philadelphia Eagles, 6'5", and I could push down hard enough, I'd break the table, right? So if you put enough stress on rocks, they're going to break. That's when you get an earthquake. Another way of saying it is, wherever you have these plate boundaries, these red lines, that's where you have earthquakes. You see how useful plate tectonics is? It tells us where 99% of the world's earthquakes occur where you have these red lines or these plate boundaries. Another thing that you want to know about are these red, see where you have these red triangles on the plate boundaries? Those are places where you have these red triangles where you have deep ocean trenches and subduction. Subduction, you might recall, is where you get oceanic lithosphere subducting under the trench, and that oceanic lithosphere melts, making volcanoes. So why do we have volcanism off the west coast of South America, the west coast of Central America, the west coast of North America, the Aleutians to this part of Russia here called Kamchatka, Japan, the Philippines, New Guinea, New Zealand, on the so-called Ring of Fire? Because that's where you have your trenches. So you also have that here in the Mediterranean area, going all the way from Italy to Turkey, so, and Iran. So this single map of the world showing you the plates and the plate boundaries is so valuable to geologists. It shows you where the world's earthquakes are, wherever you have the red lines, and it also shows you where the Earth's volcanoes are, wherever you have deep ocean trenches and subduction, which is basically the Mediterranean and the edges of the Pacific Ocean. We'll go more into that later on. Here's another picture. And here you can see lots of, it might look complicated to you if you haven't taken geology before. But think about things the way Andrew Carnegie thought about them. When presented with a complex problem, break it down into little digestible bits and understand those bits one at a time, and then you'll understand the big picture. So let's try and do that here. Here you can see a continent. Here you can see a chain of islands. Here you can see seawater in blue. The stippled pattern here shows you continental crust, and here too on these islands. Here you can see mid-ocean ridges. That's a divergent plate boundary. That means the plates pull apart. And you can see it over here as well. The plates pull apart here from that heat in the mantle. Here you can see subduction here, here, and here as oceanic plate sinks deeper into the mantle and melts to make volcanoes. We'll talk about this more later on. Let's talk about one more thing here and then we'll call it quits for this week. I wanted to talk a little bit about organic evolution, which the Brits call biological evolution, and the history of life. Historical geology is a lot different than physical geology because we focus a lot on biology. Biology is the study of living things. But in geology, we're not We're mostly interested in ancient life. And the study of ancient life is called paleontology. The study of ancient life is called paleontology. Paleontologists are people who study paleontology, and they study fossils. Fossils are evidence of past life preserved in sedimentary rocks. Fossils are always preserved in sedimentary rocks, never in igneous or metamorphic rocks, only in sedimentary rocks. So, in 1859, an Englishman by the name of Charles Darwin proposed a theory of organic evolution through natural selection. That's the word there, natural selection. And we'll talk a lot about how he got to his idea and everything. I did want to state something first of all, that it's a false argument to say that, in my opinion, that evolution means there's not a God or a creator. It doesn't mean any such thing. It simply means that within a species, we are of the same species. Our species is called Homo sapiens. Those individuals who have what it takes to survive to the age of sexual maturity and attract someone from the opposite sex to produce offspring with, we will pass on our genetic traits to the next generation. I'll repeat that. The theory of evolution basically states that if you are able to survive to the age of sexual maturity, attract someone of the opposite sex who is fertile and you're fertile, and you produce fertile offspring, you pass on your genetic traits. Your hair color, your eyebrow shape, your predisposition for diabetes, all of it gets passed on. In other words, only those individuals who have the traits necessary for survival and are able, and if you're also able to attract the opposite sex, you're going to pass on your genetics to your genetic information through your DNA. Darwin didn't understand DNA, but now we know it's through your DNA to the next generation. It's not even an argument. That must occur. As Thomas Paine would say, that's common sense, isn't it? So think about it like this. Horses appeared on the planet. Horses appeared on the planet about 55 million years ago. Some of those horses walked slow because they had 5 toes. Others walked a bit faster because they had 3 toes. And those that could run the fastest had 1 toe, called the hoof. Let's say, and back then there were all kinds of things trying to kill them, such as saber-toothed cats. Which horses are going to have the greatest likelihood of escaping a predator like a saber-toothed cat? The ones with 1 toe, the hoof, 3 toes, or 5 toes? The ones with hooves could run faster, and they're going to survive and pass on their genetic traits, aren't they? So now, if you look at horses, they almost all have only a hoof, right? Because that was an advantage. Only if you have, that's what we call the battle for survival. Only the fittest survive. Or let's look at rhinoceros. What's the thing you think about most when you think of a rhinoceros? It's got a big horn, right? What's the purpose of that horn, do you think? Well, obviously, one of the things that the rhinoceros is used for the horn for is protection. In the distant past, some rhinoceros had big horns, others had smaller horns, others had middle-sized horns. Let's say predators attack. Which rhinoceros is most likely to survive? The one with the biggest horns. So that's why rhinoceros have big horns now, whereas in the past they mostly had no horn or a very small horn. But it's not just that. Male rhinoceros, they have big horns, even bigger horns than the females. And what do they use them for? The same thing that deer use their huge rack for, is they rut. They battle for access to females. If you win that battle, you're going to pass your genetic information on. So let's say you're a male rhinoceros with a big horn meets one with a little horn. Who's going to win? The one with a bigger horn. And then you go over to the female and you say, "Hey baby, I got a big horn and he had a little one." I'm sorry. But anyway, you get the idea. So that's Darwin's theory of evolution, and that's all for this week.